So our final speaker in this set of talks before, after which we'll have some open discussion and then a break. Our final speaker for this set of talks is Sheng-Lun Tai. Sheng-Lun is an earth scientist at Pacific Northwest National Lab, and prior to coming to PNNL, he had obtained his PhD at the National Central University in Taiwan, where he had done some work partly on data assimilation in forecasting models, and he's continued work along those lines at PNNL recently. So he's going to share some of that with us.
Great, thank you, Stena. All right, okay. So I would like to talk a little bit about our work about simulation of continental shallow cumulus populations using an observation constraint cloud system resolving model. And I would like to acknowledge my co-authors from our lab. And this work was published on James, so please feel free to browse if you are interested. And first of all, I thought it would be helpful to briefly talk about what are the components that have been identified to control the continental shallow cumulus evolution. So as you may know, the ambient environmental sets up the atmospheric stability as well as the wind shear. And so in the model, this is given by the initial and boundary conditions. And then the incoming solar radiation could be very complicated when it goes through the atmosphere, and which is handled by the radiative transfer model here. And then in addition, the representation of soil properties and land use are important as well, as they essentially provide the lower boundary conditions in the model. With them, the land surface model partitions the sensible and latent heat fluxes and fit them into the planetary boundary layer scheme. And then to mimic, so the PBL scheme actually mimic the turbulent mixing process. Finally, as the cloud forms, the microphysics scheme and chemistry model are responsible for simulating the evolution of cloud particles. So while these components are critical, all of them actually basically take place within or just above the boundary layer. But however, unfortunately, there is actually large model uncertainty in the boundary layer. Like what this study shows, they found an overall warm bias near surface across many different weather and climate models. And they also compare the simulated temperature profiles against ARM SGP radio sound, like here. And they found that there is a robust warm bias within the boundary layer at the ARM SGP location. So here comes our approach. So our approach is to reduce the model uncertainties in initial and boundary conditions, and especially focus within the boundary layer. So by using the multi-scale data assimilation framework, we anticipate integrating all valid observations to constrain large-scale weather pattern, and then the mesoscale ambient environmental conditions, as well as the boundary layer structure and evolution. And this could then help us to understand first how improved environmental condition can influence the prediction of shallow cumulus populations, and then the transition to deeper convection. And the secondly, the data impact of boundary layer observations. Okay. So just an overview of our study case. So there was a case observed on August 30th in 2016 during high-scale field campaign which was selected for our study since a complete life cycle of shallow cumulus was occurring near our interested domain, near the ARM SGP site. And from the snapshots of the GOES 13 flectons on the left, we can see in the yellow box near the northern Oklahoma, it was basically cloud-free in the early morning. And then throughout times, the shallow cumulus populations form and transition to deep clouds in the afternoon. On the right, you can see this is a snapshot taken at 2 p.m. at local time, which provides us a detailed view on how the shallow cumulus population distributed around the ARM SGP central facility in the middle, the yellow dot shows. Okay, so to perform the data simulations, there are basically two major components. One is the model forecast, and another one is the observation. So the idea of data simulation is to optimally blend information from both model and then also the observation. So in this study, we ran a wolf model with 4 one-way nested domain with resolution from 36 to 1.33 kilometer. And then with finer resolution, vertical resolution within the boundary layer to resolve the atmosphere in the boundary layer. And as you can see, the domain 4 actually covers all the ARM SGP size, as you can see in the map here. And in terms of the observations, we assimilated conventional observations from NSAP operational data stream, such as radio sound, buoys, ship, aircraft, and radar, VAT, wind profile. And in addition, we got multiple boundary layer meteorological observations from the 2016 high-scale field campaign, like the radio sound, the Raman LiDAR, Doppler LiDAR, radar wind profiler, and also the Oklahoma Mesonet. I didn't show here. So some of them are assimilated, but some of them are used for model assessment. Okay, so talking about the assimilation package we are using, which is the community GSI. The full name is the Grid Point Statistical Interpolation. So there are several assimilation techniques can be adopted in this package, and we are using the hybrid 4-dimensional ensemble variational method because it considers time evolution of background error, and then which it was proved to be useful to assimilate high temporal resolution data. So the term hybrid means the background error actually come from both flow dependent and static type of background error. And based on the estimated errors of model forecast and the observation, GSI will be able to iteratively minimize the cost function, like what shows on the right here. So the optimal model state will be obtained once the cost function gets its minimum. And in this study, the model variables of UV, winds, and temperature, and moisture, and pressure are updated after the assimilation is done. Okay, so to understand the impact of data assimilation, we conducted several experiments. The first one, 40 in VAR, is our control experiment, which we use NSAP FNL reanalysis as the initial and boundary conditions, and then assimilate all available observations, such as the NSAP GDAS data stream, and all the ARM data, like it shows here, and Oklahoma Mesonet surface meteorology. And the second one, we excludes the ARM and Oklahoma MesoNet only assimilate GDAS operational data stream. And then third one, it's just like a pure forecast initialized by NSAP FNL reanalysis. And then the first one we introduced here because her actually provides 3-kilometer resolution reanalysis data. And also it assimilated even more data than us, like including cloud information from radar reflectivity. So that's a good reference here. Okay, here comes the results. So to have an idea how the clouds are simulated, we compare the simulated cloud fractions in domain 3 against GOES 13 retrieval. On the left, it shows the total cloud fraction, including the ice cloud and the liquid cloud. So it shows that the two 40-invar experiments reproduce comparable amount of cloud fraction with the observed quantity. And whereas the FNLBC and HER-BC actually have less cloud covers within this area. So for like a liquid-only cloud fraction on the right, it basically mimics the evolution of the shallow cumulus clouds. We can see a rapid increase of cloud cover found at 10:30 a.m., which is the arrow shows here. And so this process is generally captured by all experiments, despite some difference in timing and the magnitude. And also suggests that this rapid increase of total cloud fraction is contributed by the liquid clouds majorly, since both of them have similar growth at 10:30 in this case. Okay, then we further zoom in and focus on the simulated shallow cumulus populations near the ARM SGP site. So on the left, it's showing the MODIS aqua visible image taken at 2 p.m. local time. In the middle, the corresponding cloud water path retrieval is adopted to compare with what is simulated in 40-invar experiment on the right. So the retrieval is in 1 kilometer resolution, and then the simulation was in 1.33 kilometers. So they are quite comparable in terms of the resolution. And we were actually surprised that with 1.33 kilometer resolution, we can reproduce the major cloud features in this domain. But we can also see that there was less aggregated shallow cumulus population than what is observed in the by MODIS. And since there was a Doppler LiDAR network around the SGP site was deployed, so we were able to evaluate the simulations within these red blocks. So for example, we particularly look at shallow cumulus life cycle within the box. So the domain average cloud mixing ratio is given in the color shading on the left panels. And along with the LCL in blue dashed lines and then the PBL height in red lines. The top left panel provides the observed quantities such as the Doppler LiDAR estimated cloud base height, which is given by the dots here, and the standard deviation is showing by the arrow bar. And also you can see the yellow shading, which is the cloud masks, R-scope cloud mask. And then the stage 4 precipitation is given by the purple bars on the map here. And then I would like to draw your attention to the cloud initiation time first. So while there are about 1 to 2 hours delay in FNOBC and the HERBC, you can see the dots here actually tells us there was clouds was observed by the Doppler lidar, but you can see in these two models, in these two simulations, they didn't reproduce these clouds at the accurate time. And then we can see in the DA experiments, actually, we have corrected this bias by using data assimilation. And also, you can see the cloud-based height, simulated cloud-based height is also like too high in these two cases, but was also like a much closer in the DA experiments we have shown here. And then to understand why cause this, we further look at the moisture evolution within the boundary layer on the right panels. So we have found that the accurate prediction of moisture in the boundary layer is actually essential for better prediction of shallow cumulus life cycle. As you can see, the 40M var actually better capture the moisture evolution than the other experiments. So with this, a brief summary here. So data assimilation corrects the boundary layer stability, which leads to more accurate onset time of shallow cumulus initiation, and then also the better evolution of cloud-based height. The moisture within the boundary layer is found to be strongly modulate the shallow cumulus evolution. And then to confirm the improvement, we also look at the profiles at early morning, noon, and late afternoon. So in general, the 40M var in blue line has the best performance among the experiment, including there is a significant correction of positive bias around the noontime, like what is showing in the middle panel here. And so lastly, to test the robustness of our approach, we extended the application to a 3 days period from August 29th to August 31st. We particularly look at the forecast of cloud-based height and found the arrow actually was significantly reduced with data assimilation. So with this, I think this approach has been showing very promising results. And I would like to end here and take any question you might have. Thank you.
Great, thank you, Sheng-Lun. And I'll monitor the Q&A and chat for questions. But maybe I can just kick it off with one, which is, Sheng-Lun, you've shown us that the forecast error is reduced when using a DA, and especially the 40M var performs better than the other approaches you evaluated. Can you comment on what, do you see opportunities to then use this method to improve process level insight or other future applications for it?
So I think, the increments after data assimilation, I think that is a very useful information because it tells where the model went wrong in like a structural. So I think if we have like statistical analysis about those increments, then we might have a sense like where the model like usually went wrong in like a certain period of time, and then we can try to digging into this problem, and then we can try to focus on this certain structure in the model